In this class, we've talked about polynomial functions, we've talked about rational functions, we've talked about radical functions, we've talked about exponentials and logarithms. So now that we've talked about all those different types of functions, let's talk about finding their inverses. Okay, so that's what our focus is going to be today, is to be able to find the inverse. So I printed out the notes because there's a lot of stuff that I just kind of want to talk about, and I want you to be able to add to, but I want you to have all these words too, okay? So I didn't want us to sit here forever copying stuff down. All right, so first of all, let's talk about what defines the inverse function. Okay, if a function has the ordered pair a, b for every value of a in its domain, okay, so all the x values that it can possibly have, then the inverse switches your x and your y. Okay, I think y'all already know that. We've talked about inverses before, but you should know that inverse functions switch the x and y values. So if we have this list of points for our function, then its inverse will have these points. Okay, all it does is it switches the x and y values. Now, something to be mentioned. This first set of points right here is not actually a function. Can anybody tell me why that first set of points is not actually a function? Okay, is that why it's not a function? The problem is the -4. We have two y values for a single x value. A function can only have one y for every x. Okay, one y for every x. We can have repeated y values. That's not a problem. Repeated y values are not a problem, but repeated x values are a problem. So that's not actually a function. Is its inverse a function? Is this inverse right here a function? No. It has the same issue, but this time the issue is with -3. -3 has two y values. So I want you to make the note there that neither of these is actually a function. If something's not a function, then we call it a relation. Okay, there is a relationship between the x values and the y values, but because we have repeated x values, then we call them relations instead of functions. Okay? Now, what is the test that we use to test to see if something's a function? The vertical line test. Okay, the vertical line test is what we use to test to see if something's a function. So let's look at the next paragraph. If a function's inverse is also a function, then we call it one-to-one. Because if we've got a function, every x has only one y. So if its inverse is also a function, when we switch the x's and y's, if that's a function, then that means every y has only one x. We've got two different tests. Okay, the vertical line test tells us if the function, let me say this, if the function is a function, that's a really weird way of saying it, but if the original one is a function, okay, it passes the vertical line test. If something passes the horizontal line test, that means its inverse is a function. Okay, so vertical line test, that's what you're used to. That's to test if something is a function. Really, I guess I should say relation, but anyways. That tests to see if what you're looking at is a function. If it passes the horizontal line test, then that means its inverse will be a function. So here's an example. X squared. Okay, x squared we know is a function. Every x has only one y. It passes the vertical line test. But if we put a horizontal line on there, it's going to fail that almost everywhere. Okay, it's going to fail the horizontal line test almost everywhere because think about the square root or the x squared function. You've got positive and negative x values that map to the same y value. So when we flip those around for the inverse, you're going to have multiple x values. Okay. unless we restrict the domain. Okay, so if we say, well, let's only consider the positive x values. If we only consider the positive x values, then we're good. The inverse would be considered a function if we restricted the domain there. Okay? All right, and we already talked about this. The points above, is the inverse a function? No, it is not. Neither one of them are a function, actually. Okay. So here's just another definition here. If f of x is a one-to-one function that has a domain of D and a range of R, then the inverse function of f, here's the notation. It looks like a -1 exponent, but it's not a -1 exponent. That's the inverse notation. Notice the domain and range. Okay, the domain of the inverse is R. R was the range of the original, and a range of D. D was the domain of the original function. So anytime you're switching x and y, anytime x's and y's are involved, you can just switch them for the inverse. This is just a kind of a more mathematical definition here. Your inverse, f inverse of b equals a, if and only if f of a equals b. So here's a real number example. F inverse of b equals 7. If we know that, then f of 7 is -4. Or vice versa. If we know f of 7 is -4, then we know f inverse of -4 is 7. Again, trying to emphasize x and y values just switch places. Okay, so you can look at that in a set of points. You can look at that graphically. And then we're going to focus on the algebraic side of things here in a little bit. And then here's just a little note, because somebody every year tries to do this. Okay, it's not the reciprocal. You can't just get rid of the negative exponent. It's not a negative exponent. You don't just move it to the denominator. Okay, it is function notation for the inverse. Now, here's what we're going to focus on today. Finding the inverse of a function algebraically. This works for every single function out there. Okay. What will be different is step 3. What steps we need to take to solve for y. But otherwise, the other steps are exactly the same thing. If it starts with f of x, then just make your f of x y. Okay, it's just a fancy way of saying y. We're going to switch the x and y values. Now, the reason why I have switch in quotations is because if you have multiple x's in the equation, then you would just replace each x with a y. And then you solve for y, and then I'm going to be picky about the notation. At the very end, you need to replace that final y with the inverse notation. Okay? So, let's look at some examples. Flip the paper over. Let's find the inverse of this function. Before we find the inverse, what type of function is this? What do we name that function right there? What's it called? Is it exponential? No. It's not linear. I mean, the denominator is linear, but rational. Rational. Ratio, fraction, polynomial, numerator, denominator. We just did rational functions, guys. That was like the unit right before the, unit right before this was exponentials and logs. But right before that was rationals. Okay, so let's find the inverse. Okay, so we start with f of x. I'm just going to mark that out, put a y. Okay. Now, I switch x and y. So I've got x equals y over y plus 1. Now, here's the fun part. I got to try and get y by itself. So I've got it in the numerator and in the denominator. So first of all, let's get it out of the denominator. So we can multiply both sides by that y. So it cancels on the right side. Now, I'm not going to multiply it out. You can, but I'm not going to multiply it out right here. What am I thinking? Maybe I am going to multiply it out. Yes, I do need to multiply it out. I'm sorry. Multiply it out. distribute the x, xy plus x is equal to y. The reason why I need to multiply it out is because I need all my y's on one side. Right now they're on both sides, and there was no way to fix that. So I need all my y's on one side. So let's move this one over. Okay, subtract the xy on both sides. Now, we can't combine those. We just have to leave them the way they are. Now, we've got y minus xy. We're trying to get y completely by itself, so the only way to do that here is to factor out the y. Okay, if we factor out the y from y minus xy, we get 1 minus x is what we're left with. And then to get y by itself, we simply need to divide both sides by 1 over x. Or excuse me, 1 minus x. I don't know why I'm getting my minuses and overs and stuff mixed up. So we've got y by itself. I'm going to go ahead and replace that with the inverse notation. We started with f of x, so this is f inverse of x is equal to x over 1 minus x. Okay? I have it labeled as practice, but let's just do it together, because I feel like that was kind of confusing right there, so let's do another one. Y is equal to 2x over x minus 4. So we've got x is equal to 2y over y minus 4. So we start by multiplying both sides by y over 4, y minus 4, and distribute the x. Move the xy over. So all my y's are on the same side. We need to factor out the y. And then divide by the 2 minus x. So you can do this. You can do y to the negative 1. It's not the best notation, but we'll go with it. The inverse here is negative 4x over 2 minus x. Now, something to be noted here. Sometimes when there are rational expressions like this, if the majority of the signs are negative, then they will factor out a negative, which changes all the signs. So chances are this is what it will look like on the answer key. It will look like 4x over x minus 2. Okay, so as long as all of your signs, all of them, are opposite of what shows up on an answer key, then your answer is exactly the same. Okay, well, not exactly the same. It's equivalent. Okay, it is equivalent. It's still correct. But when the majority of the signs are negative, they just go through and change all the signs, because what they've done is they've factored out a negative. Oh, that's a minus. They factored out a negative, and then a negative over a negative is positive. Okay, so that's what has happened there. Okay, now let's look at example B. Now, to be honest, okay, there are a select number of quadratic equations that we can find the inverse of, because it can be difficult to solve for the variable. We can do it in this case because this is a perfect square trinomial. So let's just get into it, and so you can see what I'm talking about. So we've got x is equal to y squared minus 6y plus 9. If we're trying to get y by itself right here, we've got a y squared and we have a just plain y. We can't truly isolate the y unless we're able to factor this right side right here. So can we factor the right side? Yes, we can. It's a perfect square trinomial. So guess what? It is y minus 3 squared. So now, instead of having two different versions of y here, now we only have one version of our variable. So we can take the square root to get rid of the squared. So we've got the square root of x is equal to y minus 3. Now, I've been trying to stress the positive and negative when you take a square root, but we can't include the positive and the negative because then it won't be a function. We'll end up with multiple values. So we just consider the positive here. And then we've got to get y completely by itself, so we need to add 3, but make sure that it's clear that the plus 3 is outside of that square root. Okay, the plus 3 is not inside the square root, it is outside of that square root. Make sure that however you write it, it is very clear that it's outside. Thank you, Phyllis. Okay, so here's a cube root problem. Okay, a little bit different. We've got y equals x cubed minus 5. So finding the inverse here. Switch x and y. Now, this one doesn't have the problem the previous problem had. We only see one y here, so we can just work at getting it by itself. We can add 5. And then we've got y cubed. So the opposite of cubing something is to take the cube root. So the inverse here is the cube root of x plus 5. This time, the plus 5 is under the cube root because we added the 5 before we took the cube root. In the previous problem, we took the square root and then added 3. Okay, the order does matter. Okay, let's look at a square root problem. Let's find its inverse. Alright, so x is equal to the square root of y plus 7. We're trying to get y by itself. It's under a square root right now, so the opposite of that would be squaring. So we've got x squared equals y plus 7. Then we subtract the 7 from both sides. So f inverse of x is equal to x squared minus 7. Now, I haven't really brought this up before this point, but it seems like a good time to mention it. This quadratic right here would have a restricted domain. Okay, in order to be a function, we would have to restrict the domain of this quadratic. It can't just be all real numbers like it normally is. And where it comes from is that let's see here, the range of the original becomes the domain of the inverse. So let's talk about the range of this square root function. In order to talk about its range, we've got to talk about its domain first, right? So its domain is x plus 7 is equal to 0, or it's got to be greater than or equal to 0. So x has to be greater than or equal to negative 7. What's the y value when x is 7? When x is negative 7, excuse me. What's the y value when x is negative 7? 0. Negative 7 plus 7 is 0. Square root of 0 is 0. So that means, if you remember back to our square root functions when we were doing them, this is what this one looks like. It starts at negative 7, and it would look like this. So what's the range of that function? Okay, from 0 to positive infinity, or y is greater than or equal to 0. So the range of the original becomes the domain of the inverse function. Okay, the range of the original becomes the domain of the inverse. So the range was y is greater than or equal to 0. So that means the domain of the inverse is x is greater than or equal to 0. And guess what its range would be? Its range would be y is greater than or equal to negative 7. Don't believe me? Graph it. All right, one more practice problem, and then I'm going to let y'all do some practice. Okay, f of x is equal to the square root of x plus 7. Very, very similar to the one we just did, but there is a slight difference. That plus 7 is outside of the square root. So we've got to move the 7 before we square it. Okay, we cannot square it until that square root is by itself. So this inverse is x minus 7 squared instead of x squared minus 7. Okay, very slight difference, but there is a difference between this parabola and the other parabola. This parabola, x squared minus 7, looks like this, restricted domain. This one, shifted right 7. Okay, difference between those two.